All right, in 5.3, we're going to talk about binomial random variables. When the same chance process is repeated several times, we are often interested in how many times a particular outcome occurs. A binomial setting arises when we perform several independent trials of the same process and record the number of times that a particular outcome we call success occurs. So there's 4 conditions for a binomial setting. First is binary. The possible outcomes of each trial can be classified as a success or a failure, so you can clearly know which one's a success and which is a failure, and there's no other options. Independent is I. Trials must be independent, that knowing the result of one trial does not tell us anything about the result of another. N is for number. The number of trials, the chance process has to be fixed in advance. And then lastly, a success, that the same probability of a success on each trial. It doesn't change trial to trial. So, when checking the binary condition, note that there can be more than 2 possible outcomes per trial. In the pop quiz activity, each question or trial had a possible 5 answer choices, A, B, C, D, or E. If we define a success as guessing the correct answer to a question, then failure occurs when the student guesses any of the 4 incorrect answers. All right, so the count of successes in a binomial setting, in a binomial random variable, are possible values of 0, 1, 2, 3, 4, 5. These are discrete variables, okay, in a binomial setting. Now, what does the probability distribution of the binomial random variable look like? Well, any binomial distribution is completely specified by 2 numbers, okay, the number of trials and the chance process and the probability of success on any trial. Okay, so 2 things you have to know. Okay, so in this one, it's the X is the number of children with type O blood. In the probability distribution, we chose 5 children to test and the probability of 0.25 of having type O blood. So we chose 5 children and we got their blood types and figured out, okay, how many of them did have type O blood. We chose another 5, and then chose another 5. And so this is the probability over a long run, okay, of what? So let's look at this. Determine whether the scenario describes a binomial setting. Justify your answer, all right? Biologists estimate that a randomly selected baby elk has a 44% chance of surviving to adulthood. Assume this estimate is correct. Suppose that researchers chose 7 baby elk at random to monitor. Let X equal the number that survived to adulthood. All right, so we're going to use those 4 criteria, BINS, B-I-N-S, to see if it describes a binomial setting. It has to do all 4. So the B was for binary. And what that means is you have to clearly tell me, okay, what does a success mean? And what does a failure mean in this situation? Okay? We're looking at surviving to adulthood. So success is surviving. Failure is dying. Okay, not making it. I was for independence. Okay, and independence is that one success does not determine the next success. So in context, we were talking about baby elk. Okay, we would say that the survival of one elk does not determine the survival of another. Right? This is what we mean by independent. Okay? N is for a distinct number of trials. Well, how many baby elk did they choose? They chose 7. So, in this case, we know that 7 elk are selected. And S is the probability of a success. So in this case, it's the probability of survival. And they told us that. P is equal to 0.44. That's at 44% in the problem. Okay? And that probability is the same each time. Okay? So that's how you prove or justify your answer that it is a binomial distribution. Now, if it didn't meet one of those 4 criteria, then it's not a binomial distribution. Okay? So that can happen too. You just have to run through all 4 criteria before you know. Now, same problem about the baby elk and the probability of 0.44. So it says find the probability that exactly 4 of the baby elk survive to adulthood. So in notation, it looks like this. The probability that x is equal to 4. That means exactly 4, right? Now your calculator has the built-in formula for this, which you don't want to look at the formula. It's kind of crazy. But I want you to pause the video and write down these keystrokes. Now, the number of trials and the p-value and the x value change problem to problem. And I put in right here which ones are specific to this baby elk problem. But you would enter those values set differently on every problem. So pause the video to write these steps down, and then I will walk you through it on the calculator. All right, so on the calculator, when you turn it on, you're going to hit second and bars, which is right above tangent. And you get all these distributions. These are all probability distributions. But we're going to go all the way down to A. And you should see binomial PDF. Make sure you pick PDF, not the CDF. We want PDF, right? So hit enter. And then it should tell you trials. It should say trials, P, and X value. So in this case, we had 7 trials. We had a p-value of 0.44. Make sure you put the decimal. If you put a or if you don't put the decimal, you're going to get an error. Okay. And then the X value was how many do we want to survive in this problem? 4. 4 out of the 7. So we keep going, and we hit enter. And enter again, and there's our probability, 0.230. Okay. So I know your calculator's going to do it, so there's not a lot of work to show, 0.230. But you'll have to know how to get to these steps on your own. Okay? Okay, same problem, baby elk. Now it says make a histogram of the probability distribution of X. Describe its shape. Well, to be able to do this, you got to know all the probabilities for all these baby elks. Okay? So this is the probability of X, and this is the probability that 0 survive, 1 survive, 2 survive, 3 survive, 4 survive, 5, 6, and 7. So they didn't give us those, right? We have to find them. Now in the previous problem, we found the probability that exactly 4 survived, and we got 0.230. And so we're going to run through those same steps, but this time X will equal 0. Let me show you. So you're going to go to second bars. Go down to option A again, binomial PDF, and there's your trials, there's your probability, and the only thing you're changing each time when you're filling out a table is the X value. So we start with the X value of 0. And I get 0.017. Okay, so I fill in my table. Then I'm going to do the same thing, and honestly you can just do this. Highlight that line, hit enter, and it'll paste it, and I'm going to go into that and change the 0 to a 1. Hit enter, I get 0.095. Bing, copy, paste, change that 1 to a 2, because now we're saying what if 2 out of the 7 survive? And I get 0.224. And then what if only 3 survive? 0.293. Okay, going ahead, do it again. 0.4, we already did 4, so I'm going to jump over to 5. 0.109. 6. 0.28. And lastly, what's the probability that all 7 will survive? 0.003. Now, using these probabilities, we can then draw our histogram using the same skills that we used before. Okay, so let's draw this out. And my x-axis is the number of elk that survive to adulthood. Okay, and I have to go from 0 to 7. So I go 0, 1, and I look at my probabilities. Look at my highest probability is 0.293. That's as high as it goes. So probably don't need to go any higher than 0.3. Scale it accordingly. And these are my probabilities. You can make that neater. Now I draw my histogram, 0.017, that is barely anything at 0. 0.095, that's close to 1. 0.224, 293, 30, 9, 8, 7 is like almost nothing, right? So look at our shape. It says to describe our shape. Well, hopefully you recognize that this is very symmetric. So I would say the shape is symmetric, single peak at 3L. Okay, single peak at 3L. So that problem takes you a little bit longer, but be thankful you have your calculator to find all those probabilities for you. All right, so, and don't forget to label your histogram and make it neat. All right, we'll see you in class.